Alright, hi everybody. I am making this video for you guys because, as you may have noticed, somehow, so this course was originally made in Blackboard, and then I think those videos, most of them survived the transition to Canvas, but every so often one of those videos kind of got eaten in the transition, and so I don't know what happened to the audio, but it's gone. So I thought the easiest thing to do is just to make a new video here. So here it goes. So this is problem 25, which is from week 5, right? And we're supposed to use the first isomorphism theorem to show that Z mod 4Z is isomorphic to H, where H is the rotational subgroup of D4, all right? So as I think about this problem, I think, okay, so how can I find a mapping that goes from the integers to H is basically the question, because the first isomorphism theorem, as is stated here, let me zoom in just a bit, is, that's tiny, is that G mod the kernel of phi is isomorphic to the image of G under phi, right? So, and not just that, also the kernel is a normal subgroup, but that doesn't impact us much here because, of course, well, we're working in the context of integers, so it's an abelian group, and well, anyway, every subgroup of an abelian group is normal, right? But anyway, let's get to it. How do we construct a map? Well, let me just scooch this up a bit here and see if I need to zoom out a bit or not. All right, yeah. There we go. So to find a homomorphism from G, which is we're calling Z, all right, to H, which is 1r, r squared, r cubed, right? I think it's helpful to observe that these are both cyclic groups, right? So the integers are a cyclic group, and this group of rotations are also cyclic. In particular, one is generated by r, right? The rotation, if you want to think about it in terms of direct geometry, it's a 90-degree rotation, right, of the square, if I remember right. Galen's got pictures of a square and rotated and flipped over, all that good stuff in there, right? He's very geometric in his presentation of the dihedral group. But there it is. It's a multiplicative group, right? So the cyclic generators by powers gives you the whole group. And on the other hand, the integers are generated by 1, right? I guess you got two choices, right? You could use 1 or minus 1, but let's say 1, right? Just like over here, I have two choices for generators as well. I could use r, or I could also use r cubed. Both r and r cubed are generators for H. 1 is not a generator, of course, and r squared is not a generator because that has order 2. But there are two elements of order 4 in H, r or r cubed. So them's your choices. You really want to take the generator and map it to the generator. So I think a natural choice is just to map. Just a minute here, I am my own cameraman. Here we go. So to map the generator 1 to the generator R, basically, look for the homomorphism whose formula is suggested by mapping 1 to R. And so that's basically how I build formulas for homomorphisms. I look for generators in the groups that I'm looking at, or really what makes the group what it is, and I try to, if the two groups are homomorphic, I should be able to map whatever that object is in the first group to the similar object in the second group. And so that's how I build homomorphisms. I look for that, and I start there, and then I kind of build outward from that. So once you have that, properties of homomorphism, namely that the homomorphism of a product is the product of the homomorphisms, right? That leads you to, if we do n-fold additions, we get n-fold multiplications, right? So basically phi of 1 equals to r leads us to phi of n is equal to r to the n. And so anyway, you don't have to derive this, right? This is just a definition, right? So here's our definition of phi, right? I mean, this is a totally creative process, right? You could define phi otherwise and see if your phi works. But I'm going to show you that this choice does work, and it's a natural choice because, as I just explained, generators map to generators, yeah? Okay, so to be careful, I'll verify that my given alleged homomorphism is in fact a homomorphism. So if I take a and b integers, yeah, then I need to show that the operation in the domain, which is addition, maps to the operation in the codomain, which in this case is multiplication. And so that's really just properties of exponents in this context. So phi of a plus b is by definition r to the a plus b, but hey, r to the a plus b is r to the a times r to the b, which is equal to phi a times phi b. And there you go, phi is a homomorphism. I will say, I don't think Galilean actually proves that this is equal to that, right? And by the way, if you really want to get into those details, it'll take you a little bit of work to actually prove these kinds of things. It has to be done by induction, and it does involve a certain amount of nuance. I actually don't think Galilean's a good book to look at for those kind of details. You might want to look at, for example, Rotman's elementary group book. He's got proofs of like all of the basic laws of exponents in there, really, really careful. And it's a very readable book as well. Anyway, let me not write. I'll just say Rotman, Joseph Rotman. Anyway, so that proves phi is a homomorphism. So let's calculate the kernel, all right? So anytime I talk about kernel, it always makes me think of the classic Monty Python sketch where the mob is going to threaten the military and talk about their tanks and threaten them to maybe steal their tanks or something, and he keeps talking to the kernel. So that's the other, not this kernel, right? This kernel is mathematical kernel, which is, well, just a word we use to intimidate math students, right? But anyway, here we go. So problem 25, continue. We need to calculate the kernel of our homomorphism, right? So the kernel is the set of all things in the domain, which here is z, which map to the identity. The identity in the codomain is 1 here, right? So which n map to 1? So that means n and z such that r to the n is equal to 1. But what do we know? Well, we know that the order of the rotation is 4, right? So if you have r to the n equals to 1, that means that 4 must be a divisor of n. 4 divides n, right? Which is to say that n is a multiple of an integer k, right? N has to be equal to 4k if 4 divides n, right? Definition of divisibility. And hey, well, that's it, right? Right there you got, that's exactly by definition the, multiples of 4, right? The kernel is multiples of 4. It's that coset, if you will. So, yeah. Now let's put it all together. So we've got the kernel's 4z, and let's finish the thought here. So we should also mention that this homomorphism we're looking at, well, pick a point in the codomain, right? R to the n is a typical point in H, right? Notice that phi of n is equal to r to the n. Therefore, phi of z is h, right? So our homomorphism is surjective. It's onto, right? The range of phi, if you want to use sort of more pre-calculus language, the range of the homomorphism is the rotation group and the dihedral group, D4. And so the homomorphism is surjective or onto, and so finally we can apply the first isomorphism theorem, and that says that G mod the kernel is isomorphic to the image of G under phi, and that yields, in our context, that Z mod 4Z is isomorphic to H. Now, I was following instructions because we're told to use the first isomorphism theorem here, right? But the truth of the matter is, you really should, if I was just to let loose on this problem and say, how would I prove that, Z mod 4Z is isomorphic to H? I would not use the approach that's adopted in this problem. In fact, I would find an isomorphism, personally. I would say any two cyclic groups of equal order are isomorphic via the map sending generator to generator. So to me, that's a kind of easier approach. Just literally send, the generator of Z mod 4Z to H, and that would directly be an isomorphism. And this is a more general theorem. Any two cyclic groups of equal order are isomorphic via the map sending generator to generator. So anyway, Sorry the video didn't work originally. I hope I have given you enough information to answer whatever question there is in the quiz. And so yeah, that's it for this one. Thanks, guys.